Welcome to part 4 of this mini course. Today's topic is the positive mass theorem. So to start off, we want to discuss the concept of asymptotic flatness for initial data sets. If we're interested in isolated gravitational systems, then we want to consider spacetimes that are asymptotic to the Minkowski spacetime as one approaches infinity. And then for initial data sets, we may as well study ones that are asymptotic to space-like planes in Minkowski. So with that in mind, we have the following definition. We say that an initial data set, MGK, is asymptotically flat, or AF, so I'll frequently abbreviate this as AF to save a little space. If there is a compact set K, such that outside that compact set K, there's an exterior coordinate chart, right? So R3 minus a ball. And in that coordinate chart, there is an exponent Q, which corresponds to a decay rate, and the Q has to be at least 1/2. And basically, we have these equations that tell you that the difference between our metric and the Euclidean metric have to be decaying at a rate of r to the minus q. Okay, so r is just the radial coordinate in the coordinate chart. Okay, so the difference between g and the Euclidean metric decays like r to the minus q, and then this notation gij comma k, that means derivatives. So this is saying that all the first derivatives of g decay like r to the minus q minus 1, and all the second derivatives of g decay like r to the minus q minus 2. Meanwhile, we ask that the data k decays like r to the minus q minus 1, and its derivatives decay like r to the minus q minus 2. So basically, we want each derivative of these quantities to decay one order faster. Moreover, we also require that mu and j are integrable over m. So you should read this maybe as sort of two separate conditions here, and I'll discuss that in a minute. So let me say something about the decay rates. So for convenience, we use this alternative notation, which sort of captures the same equations that I wrote on the previous slide. So this gij minus delta ij equals big O sub 2 of r to the minus q. That just means that it decays like r to the minus q, and its first two derivatives also correspondingly decay 1 or 2 orders faster. And same thing with the big O sub 1 notation. The most important examples of asymptotically flat initial data actually have q equals 1. So I only said that q has to be at least 1/2. But the typical situation to focus on maybe is q equals 1. This includes a totally geodesic slice of Schwarzschild. But the reason why we use the q equals greater than 1/2 is that most of the analysis related to asymptotic flatness seems to work just as well when q is at least 1/2. So as long as we can prove theorems with q greater than 1/2, we will do so. However, I want to point this out, that even q equals 1 is not strong enough to ensure that mu and j are integrable. So the integrability condition should always be thought of as an extra condition on top of the decay conditions for g and k. This will come up in our next lecture in an important way. But for now, just think there's a decay rate that we need for g and k, and separately we want mu and j to be integrable. Meanwhile, although q greater than 1 implies integrability of mu and j, it's too strong to be of interest. So remember the important terms in mu, right? They're basically like two derivatives of g. So if g is going like r to the minus 1, then mu would be going like r to the minus 3 typically, and r to the minus 3, of course, is not integrable over r3. So that's why it's just barely on the border of not being decaying fast enough. So why do we want the integrability of mu and j? Well, it's necessary to define a notion of total energy momentum of the system. And that notion of total energy momentum that we will be using is due to Arnowet, Deser, and Misner, and usually abbreviated ADM. So the concept of ADM energy momentum, it was originally motivated by a physical argument, but here I'm going to offer maybe a different sort of motivation, I guess, a simplistic motivation, I would say. Okay, so naively, you might think of total energy E as being the integral of energy density. So energy density is 1 over 16 pi integral of mu. Actually, that's a mistake. It should be 1 over 8 pi integral of mu. The 8 pi is basically coming from, remember the Einstein field equations had a 8 pi in it. So typically, if you think of mu as energy density, actually the definition of mu, according to the correct physics definition, would actually have the 1 over 8 pi in it. In a lot of the math literature, we don't put the 1 over 8 pi in there. So for that reason, you would want to integrate 1 over 8 pi mu. Anyway, but the important thing here is that although that's the naive idea, really the concept of a total energy should be determined only by the asymptotic behavior of G and K, not the behavior in the interior. Because what do we mean when we talk about total energy or total mass of a system? That can only be something that matters to objects in physics that are very, very far away. And so essentially, it should really be a property of the asymptotics, right? Like when you say that a star has a certain mass, right? That mass is only relevant when you're outside the star. It doesn't matter when you're inside the star. So that's the reason that total energy should be thought of as an asymptotic quantity. The energy density mu can be expressed as a divergence modulo lower order terms. Precisely, mu is 1/2 the Euclidean divergence of the sum of Gij minus Giij plus quadratic lower order terms. So this comes from actually the really just the scalar curvature, right? The scalar curvature has this expression as a divergence. But then the other terms, if you go back to the formula for mu, they're just quadratic in K anyway. So the K parts don't really show up here. So we have this divergence term and we have quadratic lower order terms. If you're curious, where does the Q greater than half come from? The reason is the Q greater than half is what it takes to make sure that those quadratic lower order terms are actually integrable. So, I see there's a bit of a typo here. That sum should be I equals 1 to 3, right? Because we're only working in 3 dimensions, right? It would be n in n dimensions, but for this talk, I'm only talking about 3 dimensions. So I think, so to put it differently, in the linearized theory, where mu is replaced by its linearization at trivial Euclidean initial data. Okay, so if you linearize at trivial data, which is, I'm writing there as G sub E for the Euclidean metric and 0 for K equals 0. And then H and W here represent essentially first order variations of G and K. So if you take that linearization and apply it to HW, then you just get that divergence term. And again, I apologize, it should be I equals 1 to 3, not I equals 1 to n. There is no n here. All right. Then we can use the divergence theorem to write this as a flux integral. right? So if you did try to integrate this divergence, then that does become a flux integral over a very large sphere as that sphere goes to infinity. So this is again, it's a little bit rough, but it's one way of sort of motivating where the definition of ADM energy comes from. And so that's what we have here. So, and why does this make sense? Well, all asymptotically flat initial data is close to Euclidean near infinity. So in that sense, as we get closer to infinity, the more the linearization picture actually makes sense as a stand-in. So this motivates our definition of ADM energy of an initial data set. So I say it's the energy of the initial data set, but it has no dependence on K at all, right? It just depends on G. So the energy, again, we are integrating from the previous slide, is 1 over 16 pi times the limit as your coordinate sphere S sub r goes to infinity of the sum of gij comma I minus gii comma j times the normal. Right, so nu is the Euclidean outward unit normal to the Euclidean sphere S sub r. So again, those commas, they just mean differentiation in, like comma sub I means differentiation in the I coordinate. And again, the n should be a 3. So similarly, if you look at the formula for J, you see that J sub I is also very nearly a divergence near infinity. Again, a Euclidean divergence near infinity. So just following kind of the same idea, you can see that the ADM momentum definition should be that P sub I is 1 over 8 pi limit as that sphere goes to infinity, and now we're summing over Kij minus trace K times Gij. Again, with the normal component nu sub j, nu upper j. Okay. Now, if that ADM energy momentum, which is now like a 4 vector, right? E, P1, P2, P3, if that's future causal, meaning that the first component is like the time component, is greater than or equal to the space components, right? So the assumption is that if E is greater than or equal to the length of P, remember these are just numbers, E, P1, P2, P3, then the ADM mass is m, which is the square root of E squared minus length of P squared. Okay, as you might guess, for the short shield example, right, the short shield metric of mass m, right, it also has this mass m as according to this definition. Okay, so let's discuss the positive mass theorem now. So physically, if you assume that the sources for your gravitational field essentially correspond to non-negative matter content, right? That and then that should imply that the entire gravitational system should also behave like an object that has non-negative mass. When I say behave like an object that has non-negative mass, I mean asymptotically from very far away. So if you interpret these in the way that makes most sense, the source is having non-negative mass corresponds to the DEC, dominant energy condition, and the requirement that the whole system has non-negative mass, that corresponds to ADM mass being existing and being non-negative. So this theorem is usually called, or part of, the positive mass theorem, or it's even called the positive mass theorem. But I'm going to try in this talk to give very precise names to the theorems so that they're very precisely expressing what they mean. So I call this the non-negative mass theorem for initial data sets. It says that if you have any complete asymptotically flat initial data set satisfies the DEC, then it must have future causal ADM energy momentum. In other words, it must have well-defined mass. In this case, the way we define it, well-defined mass is the same thing as saying it has non-negative mass. So it says that E is greater than or equal to the length of P. Okay. All right. So one really important case, which is very important in Riemannian geometry, is the case when K is identically 0. This is sometimes might be called the Riemannian non-negative mass theorem. It says that any complete asymptotically flat Riemannian manifold with non-negative scalar curvature has E greater than or equal to 0. So in this case, energy is the same as mass because P is 0, right? So if K is 0, then just looking at our definition of P on the previous slide, you see, well, K is 0 definitely means P is 0. And when K is 0, the dominant energy condition is literally the same thing as saying non-negative scalar curvature. So this has a nice interpretation just in terms of Riemannian geometry. But in today's talk, I really want to focus on the initial data set version. So what's a little bit of the history of this is that Shane and Yao first proved that E is greater than or equal to 0 in the so-called maximal case where trace K is 0. So it's a very restricted case, but it's an important one, and it of course includes the Riemannian case. Since it's proved E greater than or equal to 0, one might call this like a non-negative energy theorem. And but they also had some restricted asymptotics, and this proof used minimal surfaces. But not long after, they were able to remove the asymptotic assumption by proving a density theorem. So they basically showed that the restricted asymptotics they were interested in were sort of dense in the sort of more general asymptotics described on the previous slides. And they went further, and they used the Jang equation to reduce the general case to the maximal case. So basically, they were able to prove this non-negative energy theorem in the full generality. In 1981, Ed Witten came up with a totally different proof using spinors and the Dirac operator. And that proof shows that E is greater than or equal to P. So we have the non-negative mass theorem there. Okay, but some further developments, together with Michael Eichmeier, Lan-Xuan Huang, and Shane, we were able to give a different proof that E is greater than or equal to P. And the way we did that was we start with essentially a more sophisticated density theorem. But then after that, we use an adapted version of Shane Yao's original proof. And this is the proof that I'm going to talk about today. Give more details about how that proof works. Alternatively, after applying the density theorem, one can instead apply, or actually it's a slightly different version of the density theorem, but basically after applying the density theorem, one can apply the boost theorem of Christodoulou and Omurha to directly reduce the E greater than or equal to P problem to Shane Yao's E greater than or equal to 0 theorem. So that's an alternative perspective on how one can do this. And one thing else I'll mention is again, slight alteration of the proof, is Lohkamp developed a compactification trick that avoids some of the technical complications involved in dealing with non-compact surfaces in what I'll call the EHLS proof for short. So that's the one that I'm going to discuss, and I'll when we get there, maybe I'll mention something about that, what I mean by this. And most recently, there's a nice proof by Hirsch, Cazares, and Khoury that gave a proof based on Daniel Stern's scalar curvature identity. So while Witten's proof uses spinors that solve the Dirac equation, this proof uses functions that solve like an altered version of being harmonic. essentially. So that was a recent development. So let me just say something about going beyond. I'm only been stating everything for 3 dimensions. But let me just say that Witten's proof, it works for all spin manifolds. As long as you have spinners, it's okay. And the EHLS proof was given to, it works in dimensions less than 8. Although to go above dimension 3, actually it requires some extra work, which I'll mention. And or if you prefer, you can avoid the extra work by using Locamp's compactification trick. And also, Locamp has a preprint that describes how one can get the theorem in all dimensions. Okay, so let's talk about what are the concepts used in this EHLS proof of the non-negative mass theorem for initial data sets. So there's a convenient type of asymptotics. We call it harmonic asymptotics. They're a little bit more specialized than asymptotic flatness. So we say that asymptotically flat initial data set has harmonic asymptotics if we can write G and K in a very particular way. So here we're writing G is basically a conformal factor times Euclidean space. And again, this is only in the end. So we don't care what's going on in the compact region, but outside of some large compact set, this needs to be true. That the metric is conformal to the Euclidean metric. And the second one's a little harder to maybe simply state, but K has to be given by, okay, so a corresponding conformal factor, but then times a term that arises from a vector field Y. So the exact formula is there. It says that you take the lead derivative of the Euclidean metric with respect to in the Y direction, and then subtract the divergence of Y times the Euclidean metric. Well, sorry, 1/2 times that. So L sub Y is the lead derivative, and the U and Y have to have sort of nice asymptotics. So these are asymptotics that are similar to the asymptotics for harmonic functions. That's where these decay rates come from. So U is just going to be 1, so that makes sense. It should be close to 1 at infinity. But then the next term of decay is some constant over R, and then plus lower order terms that decay like r to the minus 2. And Y sub I, same thing, some constant over R plus terms that decay like r to the minus 2. So here I've altered the notation that I had before. So instead of saying big O sub 2, I'm using big O sub 2 plus alpha. So this is a little bit more precise. The alpha here, you should think of as a Holder exponent. So it's kind of like saying, not just the first 2 derivatives are decaying in order to, but actually like also the alpha, the Holder alpha derivative of that second derivative should also decay like 2 plus alpha orders faster. So it's a little bit technical. It's not hard to sort of, write out exactly what it is, but I don't think it's necessarily worth it here. So anyway, the important theorem that we have about harmonic asymptotics is that, okay, so this is our density theorem. Given any complete asymptotically flat initial data set that satisfies the DEC, so remember the DEC is mu greater than or equal to the length of J, the point is that we can always perturb it to have harmonic asymptotics. But not only do we want to perturb it to have harmonic asymptotics, we can also perturb it simultaneously so that it has strict dominant energy condition, that is mu strictly greater than J. And also we want to do it in such a way that the ADM energy momentum doesn't change much. So it is a small perturbation, but actually for the purposes of what we're going to say, the only important thing is that it's a small perturbation that does not change the ADM energy momentum by much. Okay, so the density theorem says you have something, you can kick it just a little bit to give it harmonic asymptotics and strict dominant energy condition without changing the ADM energy momentum by much. And so it's called a density theorem because it basically says that these sort of nicer metrics or nicer initial data sets, right, the ones that have these two bold properties, harmonic, asymptotic, strict DEC, that they're sort of in some sense dense in the space of all asymptotically flat initial data. I guess I should I think I missed a word here. It should actually be there exists complete initial data that has all these properties. Okay. All right, so now let's talk about the proof. When I say proof of the positive mass theorem, I actually mean proof of this E greater than or equal to P theorem. So to prove this PMT, positive mass theorem, suppose there's a counterexample with E strictly less than P. And we're going to try to get a contradiction out of this. Well, the first step is to apply the density theorem. So what the density theorem says, well, since E is strictly less than P, we can certainly find a counterexample that not only has E less than P, but also has the strict DEC and has the harmonic asymptotic. So this is the way that we use the density theorem. So our counterexample has some slightly better properties than a general counterexample. And we can also just rotate the coordinates to force it so that the capital P, it all just resides in the third component, the Z component. So 0, 0 minus length of P. Okay, so this is why we like the harmonic asymptotics, is that the harmonic asymptotics allows us to explicitly compute the null expansion of the coordinate planes for at least coordinate planes that are very far out. So with respect to the upward normal, the coordinate plane z equals lambda, so that's the horizontal plane of height lambda, that will have the same sign as p minus e times lambda. So using our assumption, right, that e is less than p, we see that, well, okay, that's the same sign as lambda. So for large positive lambda, we'll have that the upward null expansion is positive, and for large negative, so z equals minus lambda, you see that the upward null expansion is negative. So the intuition here is that we have these two planes that they form barriers for the equation theta equals 0. So there should be a complete MOTS. Remember, MOTS is marginally outer trapped surface. It's just a surface with theta plus equals 0. So there should exist a complete MOTS lying in this slab u lambda between these two planes. So I'm defining that little red u lambda. I'm just defining it to be whatever the region is between the two planes z equals lambda and z equals minus lambda. Okay, the way we actually do this is we're going to construct MOTS with prescribed boundaries and then take the limit as those boundaries approach infinity, right? And then hopefully we'll get the desired complete thing. All right, in order to do this, we need an existence theorem for MOTS. And the relevant existence theorem was given by Michael Eichmeier. And this is the statement. So let omega gk be a compact initial data set with boundary. And then we're going to put a curve on its boundary, separating the boundary into two pieces. Which I'll just call, I mean, it doesn't matter. It's just sort of two pieces, boundary plus and boundary minus. And we have assumptions on those two boundary pieces. So the null expansion of the plus boundary piece should be positive with respect to the outward pointing normal. And the null expansion of the minus boundary should be negative with respect to the inward pointing normal. So remember, unlike for mean curvature, if you reverse the normal, it does not necessarily reverse the sign of theta, right? Because the theta is defined a little differently. So But I do want to point out that so then the result is that there exists a stable MOTS in omega with boundary equal to gamma. So it's basically solving like a MOTS plateau problem. We have a prescribed curve, and we want to find a MOTS whose boundary is that curve. Well, in order to do that, you can always do that as long as the curve can be put on the boundary of some region that satisfies these two conditions. So this should be maybe compared to, again, the null expansion is a generalization of mean curvature. So you could imagine writing this exact theorem for mean curvature, and that's a sort of that's a known theorem of Riemannian geometry, that if you have a boundary and it splits, a curve gamma that splits the boundary into two pieces, okay, and those two pieces essentially have opposite signs of the mean curvature, but with respect to the outward pointing normal and the inward pointing normal respectively, then there has to be a minimal surface in between. In fact, a stable minimal surface. Again, for those familiar with the idea, it's because these two boundary pieces, right, they form barriers. Okay, so that means that you just solve for whatever, and you know that it can't ever touch those boundaries, so there is a solution. So this is a little bit like what we had on the previous slide. I'll just say that, except instead of boundary plus omega and boundary minus omega, what I had there was the two planes, z equals lambda and z equals minus lambda. So the upward pointing normal is pointing out of the slab on the top piece and is pointing into the slab on the bottom piece. So you can see that these are the exact same conditions. The only difference is we can't apply this directly because this is a MOTS existence theorem for a compact initial data set, and the slab that we're talking about, of course, is not compact. So that's why we have to do a little bit more work. So this theorem is proved by building on Shane Yao's work on the Zhang equation. So basically the way Eichmeier constructs these is solves the Zhang equation and then observes that that where they blow up, this forces a blow up of the solution along the desired MOTS. But anyway, that's a bit of a digression. So let's talk about how we're going to use this. So in our situation, right, we have remember the slab is U sub lambda. That's the region bounded between these two planes. So for large rho, we're going to apply it to the region that is that slab intersected with, or the part of the slab that's bounded by the cylinder of radius rho. And I'm going to take gamma just to be a circle of radius rho at height 0. So that means that the boundary of omega sub rho is actually just, like a can, like a cylinder with a top and a bottom. Okay, and then gamma is just running around the center of that can. Okay, so we already saw, as I mentioned, that the top and bottom of this are basically just in those planes, and those planes have the desired signs. So those have the right signs. So we just have to make sure that we have the right signs on the cylindrical boundary. So the lateral boundary, where x squared plus y squared equals rho squared, that also has the correct sign for large rho. And the reason for that is because asymptotic flatness guarantees that the h term dominates the trace k term. So remember, theta plus is equal to h plus trace k. And the asymptotic flatness tells us about basically the behavior of these terms, and you can see, okay, the h is going to dominate, so that's how you know that the h is positive for the outward pointing normal, and it'll be negative for the inward pointing normal. Okay. Okay, technically also this boundary, it doesn't really, can't apply the Eichmeyer's theorem directly because the boundary, it's not smooth at the sort of intersection points where the cylinder meets the meets the planes, but you can always smooth those corners, and that works out okay. Okay, so, sorry, looking at this theorem, at Eichmeyer's theorem, it says there exists a stable MOTS. But this is a stable MOTS with boundary, so I should clarify what that means. We talked about stable MOTS at the very end of the previous lecture, what that means. But now let's be a little more precise. So when we say that a MOTS with boundary is stable, okay, we mean that the principal Dirichlet eigenfunction of the linearized null expansion operator L sigma, so that's the operator L sigma from last lecture, that has non-negative eigenvalue. So remember, in general, stability means the principal eigenfunction has non-negative eigenvalue. So the difference here is if there's a boundary, then we interpret it as the Dirichlet eigenfunction. So these are eigenfunctions that are 0 at the boundary. Okay, so let's talk about, so what does stability actually tell you? So let's go back to, again, last lecture. In the proof of Hawking's theorem, we saw that when sigma is a stable closed MOTS, so I'm just going to quickly summarize the argument we had, right? We had that means lambda is non-negative. That means 0 is less than or equal to phi inverse L of phi. And then on the right side there, that's the formula that we had for after rearrangement of L phi over phi. And then when you integrate that tells you that 0 is less than or equal to the integral of q. Remember, q is this quantity that it's complicated, but it's closely related to the Gauss curvature. It's less than or equal to the Gauss curvature under the DEC. So we want to do the same thing here, but actually it doesn't come out as neatly in the so this is for closed MOTS. Now we're interested in MOTS with boundary. So for MOTS with boundary, unfortunately, it doesn't come out quite so cleanly. For MOTS with boundary, why? Because this breaks down at the boundary where phi equals 0, right? You're not allowed to divide by phi if phi is 0. Right? It's a very, very basic thing. So you're not going to be able to make that argument work. So, well, we do the next best thing, which is instead we observe that for any function v supported in the interior, okay, we can now write v squared times phi inverse L phi. So again, the phi inverse L phi, it doesn't make sense at the boundary, but v squared is 0 on the neighborhood of the boundary, so that now that expression does make sense. So if you just follow that, then you can see, okay, well, this is equal to the same expression we had, but times v squared. Okay, and then by some massaging of this inequality into some rearrangement and integration, one can show that 0 is less than or equal to the integral of grad v squared plus qv squared. So actually, that's a nice little exercise if you want to see how to do it. Like look at the expression above. Basically, when you integrate that, you integrate the divergence term by parts, okay, and then when you integrate the divergence term by parts, some of it you can separate out to get that grad v squared term, but then other part will be some negative stuff or some non-positive stuff which we can ignore, and the rest will can get absorbed by the other negative term that you see above. Anyway, as I said, it's something you can maybe try to work out. But this is the inequality we have. So instead of getting 0 less than or equal to integral q, which would be nice, but what we actually get is 0 is less than or equal to the integral of grad v squared plus qv squared for any v that's compactly supported in the interior. So in particular, not 1, right? The function 1 is not compactly supported in the interior. Okay, so now let's talk about taking the limit of these surfaces as rho goes to infinity. So far what we have is, we know we have a stable MOTS in that slab, the slab bounded between the two planes, and its boundary is this circle of radius rho. So we can take a subsequential limit to obtain a smooth MOTS limit sigma sum infinity. So we have these compact MOTS with boundary, and in the limit we can get a subsequential limit that is actually I should have said complete. It's actually a smooth complete smooth MOTS with limit sigma infinity. Um, Allard regularity arguments also imply that sigma infinity is asymptotically planar. So not only is it locked between the slab, but actually it can't just be going crazy out there. It actually has to be like a nice graph out near infinity, and in fact, it has to be asymptotic to a plane. Just to technical on the technical side, actually, to make these arguments work, it's not just enough that they be stable in MOTS. We're actually using the fact that the MOTS that Eichmeier constructs, they enjoy an area minimizing like property. So if you're used to working with minimal surfaces, then you might think, okay, well, if they're minimizing surfaces, then there are some standard arguments that make these things work, and those arguments essentially will carry over as long as we have this area minimizing like property. All right, so as I wrote on the previous slide, the stability of sigma sub rho tells us that for any smooth v supported in the interior, we have this nice inequality, the 0 less than or equal to grad v squared plus qv squared. And then by taking limits, we see that the same inequality follows on sigma sub infinity. But the point, though, is that it will follow for any compactly supported smooth function v on sigma infinity, right? Because any compactly supported smooth function v, right, it will be, essentially supported on sigma sub rho for a large enough rho, more or less. So we have the inequality, but it's only for compactly supported functions. So how do we finish this off? Well, we'd like to be able to take v equals 1 in the inequality like we did in Hawking's theorem, because if you take v equals 1, right, then just plugging it in, well, grad 1 is 0, then you just get that 0 is less than the integral of q. So that's where we'd like to go. We want to say that 0 is less than or equal to the integral of q for this limiting sigma infinity MOTS. But as I said, v equals 1, it's not compactly supported, so we don't just get to plug it in for free. However, since sigma sub infinity is two-dimensional, it's possible to approximate the function 1 by compactly supported functions in such a way that this works. So this is sometimes called the logarithmic cutoff trick, and it only works in 2 dimensions, right? Basically, well, it's a logarithm. I mean, the name kind of describes it, which is that you have the function 1 and you need to cut it off to 0, but you do it slowly using logs, and the analysis works out basically because derivatives, well, anyway, it's just something that works, I guess. I don't want to go into more detail, I suppose. So in higher dimensions, though, this doesn't work at all. In higher dimensions, we have to work much harder to be able to use v equals 1 in the above inequality. And in fact, in EHLS, this was achieved by choosing the height of gamma sub rho appropriately. So what does that mean? If you think about what these test functions v represent, I mean, they represent sort of a first order variations of the surface. And so the Dirichlet boundary condition represents variations that don't change the boundary, right? So since we want variations that do change, we want variations that do change the boundary because, right, the function 1, of course, is not vanishing at the boundary. So so the idea is we want to actually pick the height of gamma appropriately so that it has sort of some improved stability property, I'll call it. Okay. In the original Shane-Yao argument in these higher dimensions, the height was just chosen by saying, just take the height that gives you the minimal surface of least area. But there is no concept. I mean, the concept of area is not as directly useful for MOTS, so something more complicated has to be done. Alternatively, so this is what I meant about the non-compactness, is that so we have this argument where you take these limits and get a non-compact complete surface. Alternatively, you can avoid this by using this more recent Low-Camp's compactification trick, but I should say that again, if you're familiar with maybe with the Riemannian version of Locam's compactification trick, this one is a lot more complicated. Okay, so with that digression out of the way, so how do we finish this off? So this is just like in the previous lecture. So once we have 0 less than or equal to q, so remember what q is. The definition of q is Gauss curvature minus some terms that correspond to the DEC minus something that has a sign. Okay, so now is actually where we use the strict DEC because we want a strict inequality here. So having the strict DEC is what tells us this is strictly less than the integral of k. And now the final contradiction comes from the fact that any asymptotically planar and connected surface sigma must have 0 greater than or equal to integral k. So we proved that basically using all this stability stuff and the strict DEC gives us that 0 is strictly less than integral k. But just general facts about being asymptotically planar is enough to show that 0 is greater than or equal to integral k. So just a quick word on why this last part is true. So to see this, let's just take the part of this surface lying in the cylinder of radius rho. That's just to get basically a compact piece of it, right? So it being a connected surface with boundary, we know that its Euler characteristic is going to be at most 1. So we can use the Gauss-Bonnet theorem to say that, okay, so just for topological reasons, 2 pi is greater than or equal to 2 pi Euler characteristic. And then the Gauss-Bonnet theorem, the version with boundary, tells us that we get integral k plus the integral of geodesic curvature on the boundary. And so here's where the asymptotically planar part comes in. If it's asymptotically planar enough that the second integral approaches 2 pi as rho goes to infinity. So remember, for just like a round circle in the plane, the integral of kappa is 2 pi. So as long as it's asymptotically planar, we'll also get that this is close to 2 pi. So then as you take the limit as rho goes to infinity, we get the desired inequality that 0 is greater than or equal to integral of k. Okay, and that's it for today. So what I will talk about in the final lecture is essentially the case of equality. What happens when E equals the length of P? So this is considered, that's considered part of the positive mass theorem as well. Although as we'll see, it's essentially a lot of different arguments go into handling that equality case.